Okay, so we are back for the second part of the lecture. And yeah, now we are going to discuss about the life annuities. So in the previous chapter, we discussed about the benefits of the life insurance and how to calculate the present value of the benefit annually or compounded monthly intervals. Uh, and in that case, I mentioned that the benefit is only paid at once. So depending on the type of the insurance, like we considered all possible ways of having the benefit payment and multiplied it by the corresponding probability of having that benefit and discounted that value to the present age. So that is the uh, net single premium of that insurance contract. So it says in at that point I mentioned that. So this is the money that we should hold at present to uh, pay the future benefit for this insurance. So that means, for an example, if someone takes 1 million coverage from this uh, policy, so the insurer doesn't have to get exact 1 million from the insured or the person or the customer. So the customer only paid a few or less than the benefit and get a large benefit for that one because the probability of having that payment during the considered insured period is very low. And also I mentioned that under the selected probabilities, always the person who uh, buys the insurance contract has a less death probability than the other people in the population. So that's how we like do the selection for the insurance. If someone comes with a higher mortality, so then we rate it and give them a higher death probability, though they have a younger age. So that is the uh, like the picture of the benefit payment, and that benefit was a one-time payment, but we didn't know the actual time, so that's why we considered the entire future lifetime and get the um, present value. And also we learned how to calculate the probabilities of the present value and also calculate the first movement and the second movement and eventually the uh, variance and how to convert those probability or the present values into using the annual discrete uh, present values. We converted it to monthly present values or the continuous present values. So likewise, we did these conversions and recursions uh, and mainly focused on the net single premium, which means the amount we should collect at present to bear that cost in future. But in practice, so we are not having the same customer, the only one customer in our like customer base. We will have different customers with different death probabilities, and eventually we can collect a lower premium from those customers in order to meet that higher benefit payment in future. Because we know that if like out of the most of the customers, we don't have any payment to pay in near future unless it is whole life insurance, which is the benefit is guaranteed. All the other cases, term life and endowment cases, the death benefit is optional. But in the endowment case, there's a survival benefit. So that means there's a payment at the end of the term, but uh, we will have it either the benefit or the survival uh, benefit. So anyway, we will have only one payment uh, in each timeline. So the life annuity says, uh, unlike the benefit payment, uh, which has only one occurrence in future, there's a series of occurrences under the annuities. That means you are familiar with paying the insurance premium monthly or annually until the coverage ends. So uh, that is a series of payment occurred during a specific time of future lifetime. So that means if you have purchased a whole life insurance, and you might have to pay only about uh, 20 annual premiums during the next 20 years, and then you can uh, like wait on the list, uh, and you don't have to pay any premium to get the benefit. So likewise, we can have define different kind of premium schemes for different kind of benefit types. So these premiums are mostly series. That means we know that. So in the benefit case, we didn't know whether benefit comes after 1 year, 2 year, or N years. But for the annuity or the premium payments, we know that we have to pay uh, one premium at the beginning of first year. Then there will be another premium at the beginning of second year. And for each year at the beginning, we have to pay a premium. So in that case, it's easy to work with annuity concept and incorporate that into this insurance framework. So we will discuss about the simple life annuities and also how to calculate the present values of these annuities. And then we can move on to how to calculate the premium for a life insurance contract using the benefit, present value, and the annuities. So that's how it's is planned for this lecture series. So let's move on to the continuous annuity part. In the whole life annuity, we can like the whole life insurance. So the coverage uh, valid is valid for the entire life in future, and the series occurs at any point of future lifetime. So we says the future lifetime starts from 0, and let's say up to n years. So then there's a equal chance of having this payment made between 0 and n, and we can say that it's kind of a rate between t and t plus dt. Dt is a small increment for the time, and the payment is $1 rate. That means the entire payment we have to pay is $1, and the rate is now $1 times dt. So if you integrate it through this series, eventually you will get the payment as $1 because we made it $1 in the level benefit. We also considered $1 benefit. So that means if the benefit occurs, the company pays $1 as the benefit. That's called the level benefit. And here the level payment or the sum of all the payments should be 1. And since it is continuous, we use this integration, and the present value of this annuity certain. So that means in here the certain word means the annuity is valid for specific time period, and after that it's 0. So in here we consider it from 0 to n. So that means the present value of the annuity certain for n years is given like a simple A. Since it is continuous, we have bar, and since it is certain for term, it's n terms. So that's how we got this notation. So it's familiar to the present value of insurance benefit notation. And as we mentioned, so the discount factor is 1 over 1 plus I, and we have to discount it back to the present time. So in here, we have the dt as the rate, so that we have to take it back to 0. So we take it pt times dt to 0. And I mentioned, so this is an integral. But yeah, at the end of the previous section, I mentioned we don't need to like stick to this integral definition, because we can have a different form which connects the present value of an annuity and the present value of the benefit payment. So this is how it works. So this integration is equal to 1 minus, so if you simplify this, it's equal to 1 minus v to the power n over delta. So delta is used for continuous interest payment. So, because I mentioned that in the empty compound case, when m goes to infinity, m goes to delta. So for the continuous case, delta is the instantaneous instant or the change of interest. And Vn is the present value of here. So if it was a benefit, so the benefit is paid at this point, and to get the present value, we discount it back to 0. That means v to the power n is the discount. So this is the z, and we say this is y. So this is capital Y, and this is z. So z is the present value of a $1 benefit in future, and Vn means the present value of $1 benefit n years ahead from now. So the present value of the whole life annuity now become y is equal to the present value random variable is equal to this certain uh, case, because tx is the time of death. So we know that we define it for certain time period from 0 to n. So tx is the future lifetime of a person who is at age x. So that means if tx is equal to n, that means the death occurs at n. So tx is the number of years this person survives for future. So that means these annuities are paid by the customer. So, and also in the other hand, there can be a different annuity that we pay premiums and the company starts a series of payment for us. So then there's an annuity. So which means we pay according to an annuity, and in return we get benefits as an annuity. So it's kind of a pension plan or something. So then throughout your first 20 years of your employment, you pay an equal amount uh, to a provident fund. And then after 20 years, the fund starts to pay for you in a constant series of payment. So that's also an annuity incident. So these annuities are bounded with two ways. At some points, the customer pays to the company, and at some point, the company pays to the customer. And but all these two payments stops when the death occurs. So that's why we take this whole life, uh, the present value of this whole life up to tx, because after that there's no payments occur from the customer's ends or from the company's end. So then this present value is same as 1 minus vtx over delta. So this is the present value of the benefit, because benefit is occurring at one time. So then it's easy. It's v to the power tx. And so you should familiar, so you don't get complicated with this notation. So a bar and t x term. So this is the present value. But in the next section, we will discuss about the present value of the annuity. So in that case, we will have a double dot and a dot, and also a bar in that case. But I will show the difference at that point. So don't get confused with the notation. So this is a present value, not the expected present value. So expected present value is the value you get after multiplying it by the probability. But in here, it's not the probability, it's just the discounting back. So then now the actuarial present value occurs. So the actuarial present value is the expectation of y, and it gives the present value times the probability of occurring that present value. Since this is continuous, so the present value is ai, that I for the ith interval, and we have to multiply it by the corresponding density. So for the density, we can have the survival function, because we know that for the future lifetime, expectation of x, we took it as x times px. So eventually we show that same as integration of px by alone. So that's how we got that value. And because we showed this one, like this is pxt mu x plus t. And in the previous chapters, we showed that this integral is same as having the integration without mu x t, just the survival function. So this is the density function. Pxt is the survival function. And then because this formula is somewhat complicated to handle with, so we always prefer to uh, go with this uh, survival function form, because there's only one function to deal with at that time. So if this was like term life, so then it goes from 0 to n. And but the other thing, we don't have to like find this expectation, because this is a linear transformation. You can see that the expectation of y is same as this is the random variable. So you can extend, so you can use this like the expression and derive the expectation of y in terms of expectation of z. So that's the easiest way to deal with. Uh, so that's why I mentioned, though these equations are like looks like complicated, so we can deal with these expectations easily with the expectation of z without having the integration over these probabilities to directly have the expectation of y. And now, mm, that's why I say, since the relationship is like this, so we can use this yz relation and get this done. So if I expand this from here, I can write the y as the expectation of 1 minus vtx over delta. And these are constant, so I can take it out. And this is the expectation of vtx and delta. The expectation of vtx, we know that. So for this one, since this is whole life, so we can have different cases. So the general equation is like this, z over delta. So if this is whole life, so you have the expected present value of the whole life, and this is the expected present value of the whole life annuity. So in this example, it says the continuous whole life annuity. So this the capital A says the present value of the benefit, and the bar says it's continuous, and X is the age. So in here, it says the continuous annuity present value of a person who is at age X. The only difference is simple A. And now in here, in the random variable, we have this certain term, Tx, and this L angle. But in here, we don't have the angle, because if you don't see an angle, and if that actually the annuity notation doesn't contains the random variable. So Tx is a random variable, but X is the age. So that means if you see the notation with age, that means a present value. If you see a notation with random variable, that means it is a random quantity, which is y. And now, so this is the expectation. But to get the variance, we cannot directly get the variance uh, as we used to take it for the uh, benefit calculation. Because if you could remember, the variance of z was for this. Suppose it is for the whole life. Then for the whole life, the variance was this. But for the annuity, we cannot get it. But the variance of y is not equal to the second movement of the annuity and the first movement square. So this is not equal for the annuity because, so here we have delta, but in here, so we have to multiply it by this delta term. So that means we use this familiar way. So variance of y is variance of y, 1 minus c over delta and 1 over delta. So we like divide it like this. And we know that variance of a constant is 0. So the variance of this term becomes 0. And when the random variable is multiplied by a constant, the variance is like the square of that constant times the variance of the random variable. So that's why we got this. So that means from here, we get the variance of 1 over delta minus c delta. And the variance of 1 over delta is 0. And for here, it's minus 1 over delta to the power 2 times variance of z. So since it is a square, so it's 1 over delta square. And variance of z is given by the second movement minus the first movement square. So then we can get this done. And we know how to like uh, change in between these calculations because from YZ notation, we knew for AX, for this one, it has to be like by converting this delta times AX, and AX has to be in here. So 1 minus delta times simple A by X. So that is directly conversion of this equation. And in the same way, so if we have an equation for AX, then the second moment is taken at the as twice as the force of interest. So this is valid for this one. So once you have these two, you can substitute in here and get this form done in here. So that's why we mention it here. So now you can see we use the same concept we were using in the previous. Yes, the new thing is now we have something called annuity, and it is a function of the present value. So the present value function of an annuity is a function of the present value of the benefit. And if we know how to calculate the present values of benefits, so then we can convert uh, that in linearly to have the present value of the annuity because it's a linear relation they have. So let's quickly go to this example and digest this concept. So we are given a constant force of mortality and the force of interest is delta, and express the following terms in terms of mu and delta. So when we have a constant force of mortality, we saw that the present value of A, if you could remember, so I'm not like giving this concept as since we like recently discussed this thing. So the present value of the whole life continuous was like this. So we knew this. And if you know this, you can get this directly by the YC relation using this. Then you can find this one. So that is uh, the way to use this or these kind of calculations without doing proof. But in here, it's kind of the first question that we are trying. So let's go to the fundamentals and do it as a proof. So by definition, AX bar should be from 0 to infinity and VT times PX T dt. So that was the definition. And now we can simplify this. So when we are going to simplify this, first we need to find the value for PXT. So we are given the delta for VT. And we can find the value for PXT since we know mu is constant. So for VT, it's delta T. And for PXT, is e to the power minus mu T dt. So now we have minus T times delta plus mu dt. And since it's an exponent, the final form should be given like this and like this. So in here, when we substitute infinity, at negative infinity, the value of e to the power negative infinity is 0. The function goes to 0. And at 0, value is 1. So that means you will get 1 over mu plus delta. So you get the same answer using the conversion or using the fundamentals. But if you are asked to uh, like show something or prove, so you need to stick to the fundamentals. But if you are asked to calculate these things, so the value directly, so then you don't have to do the calculations for the proof. You can use this uh, definition and do it by in quick steps. But it depends on the type of the product. So these are standard products like the whole life, term life, and the other things, but with the level benefits. But if the benefit is changing in different ways, so then you have to come back to basics and derive it from scratch. So that's the concept. Mm, Then for the part B, the variance of phi. To find the variance of phi, so we have two ways. So this is the present value. We can find the second moment and then get this equation. So we show, uh, we discussed that um, the variance of I cannot be taken directly from here. It should be the variance of z over delta square. So that means first we need to find the delta square or uh, the second moment of benefit and then use it later. So the way equation for variance of y was like the second moment of the benefit present value and the first moment of the benefit present value to the power 2 and delta square. So delta square is a constant and we know that. And under the constant force of modality, we know AX bar is mu over 2. And what we need to do is to get the second moment, just double the force of interest. So it's 2 delta. And for this one, it's 1 the square. And we can simplify it further. So if we are given the numbers, we can simplify it and get the and so this is just the um, form of the equation, but we can substitute values and find these numbers in practical cases. So that is the story of these annuities. Now you can see that the annuity is a continuous, it can be continuous or discrete. So we will discuss the discrete part in future. But for the continuous case in here that we have discussed, so we show that it's easy to work with the conversion YZ relation. So once you identify the I and the force of mortality, so and the type of the insurance product, you can find the corresponding net single premium, and then use the conversion with these second movement substitutions to find the variance and also the expectations of the annuities using those equations we have discussed. And what you have to do is like just memorize when it becomes constant force of mortality, how the future benefit occurs, and the present values occurs, or the form of the present values, and how to deal with that one using these conversion equations. Now, so that is the story of mm, the whole life case. Let's say, like in the term life insurance, so we have a temporary life annuities. So in that case, in the term life insurance, we said that if the death occurs between a certain period, let's say from 0 to n years, the death benefit is paid at that time. After that, they don't pay any death benefit. So like in here, the temporary life for a given period, uh, so we have to so the as the customer, they have to pay their payments to that period, and after that period, you don't have to pay anything, and until you live. So which means if that customer is alive during the entire period, so then they have to pay all the due payments during that time. But if the death occurs before the end, so then the payment series stops by that time. Uh, so the present value, like in Z, we can divide it into two cases. So the maximum, so in here, we know that from the future lifetime random variable grows up to n, if death occurs between these cases, suppose if death occurs at tx, so then it is v to the power a dash tx term. But if they survives, let's use blue, if they survives, so then it's vn, because after n, there's no payment. So that's why the present values should be like 1 minus Vtx over delta and 1 minus Vn over delta, depending on the time point of death. So, so if you could remember, this is similar to the concept that we used in the benefit present value calculations. And now let's get this expectation over the time from 0 to n. So here we have these the temporary life annuities of a person who is at age X for the next year. So now you can see in here also we have X, which is the age. So that indicates this is the present value, not the random variable which contains the present, which means Tx. So Tx is a random variable. That means if we define an annuity using Tx, that annuity also a random variable. If it is n, it's also a value of the random variable. So it become a random variable, but it eventually become constant. But in the present value case, it contains, so it calculates, so considers uh, different possibilities. So that means starting from age X, so it takes different ages and calculate the values. That means whenever you find X or age with the notation, you have to say, yes, this is an annuity present value, not the annuity uh, or certain annuity random variable. So this is the temporary life annuity starting from age X, goes for next n years, and it is continuous. That's why we had this bar. And if we get the expectation, so now, like in the term life benefit, the integral goes from 0 to n if the death occurs between 0 and n. But after that, there's a certain payment at age n, and then you have to discount it back. So that is the that was the motive during the benefit. So in here also, so this is the density fxt. This is simple f, and this is the survival probability up to t. And if they survives, so then there's a random variable discounted back to uh, 0. So this is discounting back to 0 continuously from 0, starting from 0 to n. So just before n, this ends, and then at end, so that means you are coming from this n, and just before n, integral stops, and at the point of n, you get this. So that's the meaning. And this is says, so we have small, like very tiny slices of these. We are just putting it together and taking the whole length. So summing up, small uh, amount of money that we have been paid continuously at more time limits, and then integrating it by multiplying after the density of that distribution. So this delta t is considered as a small time, and now we can simplify this into that known form. What's that? So this complicated form is same as the discount factor at that time point t, and the density is being replaced by the survival probability. And this is the small time interval that we are summing up over. So this entire term become this, like in the benefit payment. So in the benefit payment also we had this similar thing. And so this is the discount, expectation of the discount. But if we were only considering the expected future lifetime, so then we have to drop this discount factor. So then it will give the expected future lifetime during B0 and N. So that's the meaning. And with the YZ relation, we have seen, we can do this as well, because if we can recall the Z for this one, it says VTX for Tx is less than or equal to N, and Vn if Tx is greater than N. So that is the certain case. So you can see if this one occurs, like for Y, it's 1 minus C over delta. That's how we got this one. So if this relation occurs, so then first we can find this discrete or the continuous case. Considering the continuous case, we can find the present value of starting from x to n, and then we apply this YC relation and get the continuous expectation of the annuity from x to n. So that's the easiest way. So in here also I should mention that the endowment, the insurance benefit is $1, and we consider that we paid it over n year. $1 is being paid by dividing it to small pieces and continuously paid until we uh, ended up by paying $1 in future. So that's how it works. And for the variance calculation, again, the similar formation we need to follow. So the variance of y divided by delta. So now the product is term life. That means the variance of y is being written in terms of the uh, like the temporary life annuity. There's a like there's a payment at the end of n year. So that's why we written down here. So this C is corresponding to the present value of the endowment insurance, not the term life. So that's why we wrote it down like the variance of the endowment divided by delta. And then you can use that notation for these cases. So in here, you will have the present value as 1 minus delta xn, and the second movement like 2 times delta axn. So if you replace these things, then you can have this equation as well. So that's how it works for temporary life annuities. And then we can move to the deferred life annuities. So you will understand why we get this payment at the year of n when we are discussing the discrete case. So it's easy to visualize that concept when we discussing the discrete case. So I'll explain it again at that point as well. So in the deferred whole life, it's same as the deferred whole life insurance benefit. Um, the Y is 0 for years less than n or equal to n. But after that, there's a value, but that value is represented by the whole life minus, and in here it's as a annuity certain, and it says you are having this kind of to have a continuous payment up to tx, and you have a continuous payment up to n. So if you get the difference, you get ATX, the present value is given like this. So that's how we got this one for ages greater than tx. So the future lifetimes greater than tx. So because the payment start after n years from now. And for the expectation, so we can say this has to be like we showed it in other cases as well. So it start from the scratch and we do the integration. So integration means we can start from 0 and go to the infinity, but we know that from 0 to n, we don't have anything in between. So this is same as n to infinity vt pxt dt because of this. And you can use this YC relation uh, to find this value, but also you can use the fundamentals and find this y square and get this one, because uh, for this one, since we don't have this part and we know how to evaluate these things. So let's say if we have y square, that should be from n to infinity. The value of this one is dx and n, and it has to be squared. And the probability of having that one is px t. And the density is taken by multiplying with this. So now you can simplify this and get a familiar notation for the cases. So we know that if for this one, so we integrate this part by once and then multiply it by only the survival function and do the integration. It gives the same value. So once you do this, you can get this here. But we don't have to worry about that uh, because like we can use that YC notation and get the so we could use that YC notation and get these values for the the previous two cases, like the temporary life and the whole life annuities. But in the deferred life, we cannot get it simply. So that's the problem. So uh, which means we have to get this in a different way. So this is the first, that's why we had to get this. So this is the first movement and this is the second movement. And if you get the, so this has to be Y. And if you get the second movement and the first movement, you can write down the variance using that equation, which is given like Y square square. So this part is in here and this part is given in here. So if you simplify this, like in here, you will get this. And so you can clearly see it because once you distribute it to here and here, you have two terms, this one and this one. This one starts from 0. So that's why we don't have this discount factor. But this one, it has to come back uh, because it's deferred. So that's why N is there. So now we can think about the actual present value of MES deferred N-year temporal life annuity as well. Because in the annuity, we can define something like this. It says from 0 to M, there's no payment. Between M and M plus N, there's a series of payment in here. So that means annuity deferred for M years and then continues for N more years. So the present value is integrating it from M between M and N plus N with this VT PXT. So that's the fundamental. So we can stick to these fundamentals and find this uh, first movement and the second movement for deferred life annuity. So it's not simple as the certain and the temporary life, which means the whole life and the temporary life annuities. While working with the certain annuities, in here we have to stick to the fundamentals and do the calculations. Then there's a combination of these certain and life annuity. So in the certain, it has the same meaning. So there'll be a fixed payment during the first N years. After that, there'll be a random payment. So that means during the first N years, definitely there'll be a payment stream. But after N years, the payment stream uh, stops with the death. So it says like we can draw it something like this from 0 to N. During this period, the payment is $1. No matter what, the death occurs in between ages, the payment continues up to here. And after that, if the payment period, the certain payment period exceeds, and now the death occurs in here, the payment ends at the death. So that's the meaning. So if the future lifetime is less than N, still the payment continues up to N years. But once the lifetime exceeds the N and death occurs after N years, the payment stops at the death. So that's the certain. So this is certain. This is life. So it's Y, certain, and life. So the random variables, we know familiar with this one. For certain annuity, random variable, and this is certain, but in here for N years, it's fixed. In here, it's not N years. It will end up with the death. So the notation says present value of a continuous annuity, and it has a term of n and then continuous. So certain and whole life. So we have two bars at there. So the present value of y, this is not c, this is y, and it says the actual present value of these two cases. So this is a certain value. This is not random because it's it doesn't stop at the time with the death. So it continues up to n. So that means this is a fixed value. So that's why you cannot see any age there. But in here, it contains a deferred whole life annuity. So we can say something like this. How can we get this one? I will do it like this. So in here, for an, I can say it's a certain annuity there, and after that, nothing will be paid. So this is same as this. For this, it says there's a certain part, but after that, start a random. So it's like, so now you can see, if you simplify it just get a tx. So I modified the same version into two cases. Now you can see I can replicate this certain and life using a certain annuity and a deferred whole life annuity. So this certain annuity is Vn delta, and for this one, we can get it by the fundamentals in here. So integrating it from n to infinity, the Vt times Pxt. So that's how we get this one. So n to infinity Vt times Pxt dt. And since we showed this like this, so we can write the y as certain annuity plus another random variable, which is the deferred whole life random variable. So now when you are taking the variance, since an is a constant, so variance of y is variance of y1. So the variance of y1 is given in here. We used it, we derived it using the scratch, and you can replicate it in here. So now you can see the variance of a certain and life annuity is same as the variance of deferred life annuities. So, but the expectations are different. The variance is same. So that's a good point to remember. And now we can think about the M-year deferred in terms as well. So also again, uh, under this coverage period, if we deferred it for M years and N-year temporary life case, just integrating in between M and M plus N with the same case. So it's just a reminder of that one. And we can move to the example we have in here uh, for a certain life annuity, certain and life annuity. And we have a person who is at age 60, and we have given survival probability from 60 to t years as an exponent function with in this format. And this is also given the force of mortality is constant, and we are given the delta. YB, the present value random variable for 10 years, deferred, fully continuous, whole life annuity. So we need to calculate the expectation of Y and the variance of Y. So the expectation of Y is continuous, and we can say, let's say, yeah. Uh, so I think there's a difference in the notation. So we are discussing about age 60, so it has to be age 60 and deferred for n. And this is deferred whole life, fully continuous. So from 10 to infinity it goes. And Vt is E delta t. Pxt is given in here. P60 t and dt. So from 10 to infinity, we have, so with this notation, since they have given this, we can write down uh, this one as mu t. So for this, it's mu plus delta, so 0.05 plus zero point 0.1 t dt, and we were familiar with that one. So it's 0.15 times 10 and 0.15. So this is 75. And to obtain this one, so if you could remember the deferred whole life case, so this is V, the A dx minus AXN. So then this is V dx, and for VXN, it's 10 years Vn over delta, and delta is given. So this is V is minus delta times T. So it's delta times T over delta, which is 2. And then we can have, so let's try to calculate this one. Yeah, so let's say this is not y directly, because y had a certain part and this one. So let's say this is the present value of this deferred whole life, and this is the certain part. So now I can say 60 for 10 years certain and life is equal to certain plus deferred for 10 years. So that it's 3212 plus 1.4875087. And to get this. Double the force of mortality. So the equation for this one is this. The force of mortality part in here. So that means double means 0.2. So this one is equal to E 0.05 times 0.2 times 10. And since we double it, 0.2 plus 0.05. So altogether we have 3283. Once you have this, the variance is 2 over delta, and V10 with 60 deferred for 10 minus A N. So this is the equation, the first movement and the second movement of this one, plus the V, it's like the minus the first movement square. So the square. We have these values. We can substitute it from here. We have this one. We have this one. We don't need this one actually. Now we have this one, and we have found this one, the second movement. So we have the second movement here, the first movement here, the first movement here, and delta is given. V10 is e to the power minus delta t, and you can find it by substituting in here. So the question should be modified to 60 in here. And because it's in 16 here, and we didn't use this because this was given, I think, actually we don't need this. So you can just like forget about this part and follow the rest of the part, and then you can practice how to calculate this complicated thing. So this is the complicated part. All the others are easy to work with. The certain and life, uh, it's given in here. So the variance of certain and life is same as the variance of deferred life annuity. But for the expectation, it's the certain plus the deferred life annuity. So that's the complicated thing. So if you can digest this thing, so then it's just like you are capable of calculating the certain annuity, and you are capable of finding uh, the certain and the remaining life and the deferred life annuity values. So those are for level annuity payments. Like in the increasing benefits, we can have increasing annuities as well. So if it is continuously increasing, previously when the level occurs, this t was 1. Now it's t and increases with the t. So we just need to multiply t by v to the time t v to the power t and the survival probability, which is pxt. Then you directly get the value. And for n years term, so integral goes between 0 and n, and it's like direct application. But unlike the other cases, so It's easy to work with. Whole life and in year temporary. So for these cases, we can directly get the values, part uh, for expectation and variance, but for the other cases, as we have seen, so we have to use this integration and get these values uh, by performing the integration. So I'll quickly uh, recall these things in summary so that you can use it. So for the whole life, the notation was continuous whole life, and expectation was taken from 0 to infinity by multiplying Vt with Pxt, and O, we could get it like this. For the variance, so this is expectation of Y. This is Y, and this is, so this is the notation, and this is the expectation, how we took this. So this is same quantity, and this is the calculation. And for the variance of Y, again, it's the variance of X, expectation of X to the square divided by delta square. So that is the easiest annuity that we can work. And then temporary, we get the term like continuous. And for n terms, the equation to get it between 0 and n, Vt, Vxt, dt, O minus xn, this one. Again, just the linear conversion of YZ relation. But after that, we cannot use the YZ relation directly. So for the rest of the types, in a deferred case, the expectation notation is this, but it goes from n to infinity, Vt, Vxt, dt. So this is the expectation, but for the variance, you just need to um, use the second movement and then use the first movement square to find the variance fundamentally with the first principles. So for the second movement, you just get the square of this one and multiply it by this, get the integration. And in year certain and life, it says to n year and certain. It's the combination of certain plus deferred life. Again, for variance, find square, then variance of y is this. So for this one is also it's same. And for increasing case, we summarize increasing whole life, it's I, and increasing for the whole life. So now it's simple A, and This goes from infinity. Since it is increasing, v times dvt pxt dt. And increasing temporary life, increasing an annuity. This goes from x to n. Same integral stops at n pxt dt. For the first principles, just find this way. So that's the summary of continuous case. Now you can see, uh, unless it is a whole life or any temporary annuity, it's hard to work with the certain and life and deferred life annuities because we cannot directly relate this YZ relation for these cases. So we have to use the first principles and do integration to get those numbers. So in exam, there's a possibility of having whole life and any temporary, but we are not focusing on increasing or deferred and also certain and life annuities. So with this concept, we can move on to the discrete case. Because in this discrete case, it's easy, and we know for in the previous case, when it's continuous, the integration of this continuous density from between 1 year is 1. But in the discrete case, we can have $1 at the beginning of each month. So each year. So $1, $1 for the rest of the life. So that means it's easy to work because we know a discrete time where the payment occurs. So, and it starts with 0, which means at the beginning of each year. So we call it annuity due, which means by the time of the start of the first year, we pay the annuity. Uh, Therefore, like we have already paid for the upcoming year, and after that year end, we pay the next payment. It is for the next year because it's just before the starting of an year we pay this annuity due. So it means annuity due says we pay at the beginning of the year. So for the upcoming year, we have paid. For the annuity immediate, which will be discussed in future, it says we pay after the year end. So immediate after the year ends. So this is just before year begins. That's why it's due. And for immediate, it's after the year. Due is before the year. And that's the jargon. Since this is discrete, then we don't have bar over the notation. We have two dots. So for due, we have the two dots. But if you could remember, the last page of the previous chapter, we had annuities with two dots and annuities without any dots. So annuity notation with two dots says annuity due. Annuity notation without dots says annuity immediate. So this is two dots over A and for certain in life. That means the summation of the discounted payments during this. Since it is starting from 0, so K is also 0, and at each K, there's a payment up to n minus 1 because the nth year, if I continue it to some point, uh, at the nth year, it begins right after the end of n minus 1 year. So at that point, the payment occurs, which means the current random variable value at that point is n minus 1. That's why it's given here. This is for n terms, but it can be like extended to the whole life. The difference is in the continuous case, we divide it by delta. In here, we divide it by D. It's the discount. So V was 1 over 1 plus I, and D is I over 1 plus I. Now you can see if we get the relation, or recall the relation again, D is 1 minus V. So that's how we get this one. And when it's come to the whole life, so we don't know the actual time. So in the continuous case, we had Tx, and in here it's Kx plus 1, like in the continuous or the benefit payment also. When we were dealing with the curtailed life random variable, it started from 0 and grows one by one. Because of that, when it's come to the present value, we added 1 to that. So in the same way, we do that. That's why we could get this present value random variable in here. In that case, we added 1 because the payment or the benefit was paid at the end of the year or the considering period. So in here also, since it is due, we start with 0 at payment 1. But for the YZ relation, to stick to the same case, we have in like this. So since 1 minus this one gives that additional 1 in here, and then the present value there. So T is the discount rate. So now you can get the visualization like this, starting from 0. The Kx is here. The death occurs in here. So this is Kx plus 1. The payment has already paid for this one. So we have 111 series up to Kx, and there's no payment after the death. So we had Kx plus 1 payments because start payments from here. That's why we had K plus 1 in here, but the K plus 1 in here, because of the payment or the benefit is there for the insurance. And the annuity stops in here, but the total number of payments is equal to K plus 1. That's why it's in there. So now for the present value. Since we know that this is going to be a whole life, so the first payment comes at K equals 0. If alive, that means from X to 1, if alive, there's a one payment discounted back by one jump. If survive for 2 years, so then the probability of X to 2 and discount back 2. Then for 3 years, survive for 3, take it back by 3 jumps. Since the payment is $1, we don't have to multiply it by 1 every time. And this continues to the infinity. And now you can see this is same as this, because when K is equal to 0, P x0 is become 1. And V to the power 0 is 1. So 1 is placed by the same notation. So we can say this V0, Px0. So almost sure that by now the person is living. So the probability is 1. This is 1. So then we can summarize this as the infinite sum of v to the power k times p xk terms. So that is easy explanation for this one. So for the infinity, depending on the process, it can be replaced by uh, the remaining years of life, using the maximum number of years that we can expect for this process, which is omega. So if we know the omega, then the process stops at some point in here. So that is kind of an additional information. So be careful when you are defining for term insurance and for omega because I mentioned it even in the continuous case. I'll say why we need n minus 1 terms, because just before the final year, we pay the final payment. So then during the final year, we don't have any payment. And at the final year, the end of the final year, there'll be no payments because that is the final payment. So then if there are n years, so then since we are start paying at 0, so we just want to continue the payments until the end of n minus 1 year. So the total number of payments will be n, but the payment schemes end at n minus 1. So that's why it's there. And using the YZ relation, we can directly say that this one, which is if this one is corresponding to a life annuity, then we can find this expectation using the discrete whole life present value divided by t. So that's why it's here. And for the variance, again, like in the previous case, the variance of y is variance of 1 minus d minus c over d. The variance of this part is 0, and this one is d square over variance of c. Then variance of c is this. That's how we got this. So that is for the whole life. Now for the term life, it's same concept. For the term, so we have a term life insurance where the benefit is paid during 0 and n year, but for the temporary annuities, we always have one payment at the end of there. So which means annuity starting here and continues up to n. So like let's visualize it in here, the first case. Uh, the death occur in here. So then kx in here, kx plus 1 in here, and the final payment occurs in here. 1 up to this. And here we can have after n years, the death occurs somewhere in here, but the payment continues to here. That means there are two possibilities. We goes from here and here. So during this, we have total in payments starting from 1 to n minus 1. So 0 to n minus 1, the total number of payments is n. But in here, start from here and goes up to number, which means the number of payments is equal to kx. And that's why, so in here it's a random case, but in here for sure we have n payments. So that's how we got it. So if the death occurs before n, it's a random part, but if death occurs after n, it's fixed. We know they have to pay n number of payments. That's how we, for temporary cases, that's how we got, so because this is directly involved in the number of payments. But in the benefit case, since there were only one payment made by the company to the customer as the benefit, so the benefit occurs in between 0 and n. But in here, the annuity, in the case of number of payments, if they survive, they have already paid n payments. But if they haven't survived, they have paid kx times number of payments. So that's why we have these two cases. So in the continuous case, D was delta and Vn was same, but in here it's Vtx. So that's the difference. So like in the whole life, if I continue this, it says at the first year, I have, so in here, we have the final payment at this n minus 1 point. So in the first year, I don't have any like uh, death probabilities. Then I have to survive to pay the next. Then survive 2 years to pay the next one. And to pay the last one, which occurs in n minus 1 years, I have to survive n minus 1 years. Because after that, the final term occurs and stops the payment schemes. So now you can see the difference in between temporary annuities or the annuities and present values of benefits. In cases, the benefit is bounded with the death probability. But the annuity is always bounded with the surviving probability because any kind of part in the payment scheme keep, so which means if the customer is alive, the payment scheme is there. Otherwise, uh, it will not be continued unless it is a certain. So in here, it's a temporary life. So we have this one, and you can see k starts from 0, so that and goes for n minus k 1. So that's why it starts from 0 and goes to n minus 1, the same term as the whole life case, but it stops from here. So if we had the limiting age omega, so then if the maximum age is omega, is the maximum age, so then this person has this much amount of remaining time, and the summation become k from 0 to omega minus x minus 1 terms. So that's the difference when you have for a whole life case, if you have the limiting age or the final maximum age, so you can get the whole life value like this without going to the infinity. And we can apply YZ relation directly in here as well. So then it says the expectation of temporal annuity can be calculated using this has to be this. So this is not term, this is the endowment, like in the continuous case. So the discrete endowment of n years is used to calculate the temporary life annuity. So in discrete case. In the continuous case, we use the continuous endowment in here. That means, like in the continuous case, we can find the variance, like this is the variance of y is variance of z to the divided by d square. And only for temporary annuities and whole life annuities, we can use this YZ relation. But after that, we have to stick to the fundamentals as we have seen in the continuous case. So we don't need to like go through one by one. So there, we know how fundamental works. It's pretty much similar to the continuous case. In the continuous case, we had this integral. Now we have the summation. Limits are same. For the deferred whole life, the age is x, deferred for n years. That means the integral was going from n to infinity. In discrete case, summation goes from n to infinity. The term is b to the power k times the survival probability. And certain and life, it says certain annuity plus the deferred annuity. So for the certain annuity, again, this says this paying n amount of payments for sure. So that means for this term, it's 1 Vn d square. So for this one, we can get from the fundamentals. And for the increasing, again, instead of t, we are multiplying it by k plus 1, and k goes from 0 to infinity. And in term case goes from 0 to n minus 1. That's the difference. So that's solely for your like the knowledge. And so like in the continuous case, we apply only this YC relation for whole life and any temporary life. But for all the other deferred life, certain end life, and all the uh, increasing and decreasing cases, if we need to stick into the fundamentals or the first principles and then derive these equations from scratch. So that's the uh, story of the annuity dues. So we can finish the lecture today with this example. And there they have given a table with the number of survivals and I. So we are asked to find the annuity immediate uh, of a person who is at age 90. So this is a whole life annuity, and but it's discrete and it's annuity due. That's why we have two dots. So it says, so we can see that in this table at 90 we have 100, but at 94 we don't have any survivors. So the limiting age is 93. So that means the summation goes from 0 to, this is the maximum age, and this is the current age minus 1. So 1, 2, 3. Those are the three jumps, and 0 in here also it goes from 0, and because the payment start from 0, so we have 4 payments with 3 jumps. So here it's like this. In the first year, payment occurs at 0. For the second year, payments occurs at the end of 90. So which means at the end of 90, that means $1, take it back, and the probability of surviving from 90 to 91 is 75 over 100. And then, so we have one payment here, one payment here, one. So those are the 4 payments. And for the third payment, it occurs at the end of the second year, and surviving from 90 to 92 is 50 over 100. The final payment occurs at the end of 92, and we have to take it back by 3 jumps, and the surviving from 90 to 92 is 25 over 100. So you can get the value as 2.36. And that's the part A. For part B, it's given in here. So now it's limited for 2. We knew that. We had only 4 payments. And this says from 90 to 2 more years. So which means 1, 2, and 3. Just consider 2 cases. So K starts from here. N is 2 minus 1. And so first year, second year. So this one belongs to the next year. So this one is for the first year. This one is for the second year. And this is for the third year. And we are only considering about the next 2 years starting from 90. So that means we just consider these two payments. And the equation says one for this one and one payment in here after 1 year. That means we have to take it back from here, and surviving for that payment is here. Now you can get it as 1.707. So it's easy to work with, but unlike the benefit payment of death, so these are sequences, and always the due start from zero. So that's why we need to keep in our mind. So without, like, if we could identify the maximum number of years for survival, we can like put it there, and also if we know the end, we can put it there. But if you don't know, so if you couldn't remember these equations at time, and if you're not sure about the form, we can stick to the fundamentals and derive this by our own, because we know that for almost sure there is a payment at the starting point of the year. So we will discuss about the whole life and the temporary annuities in this course mostly. So that's why we get these two quantities for this example. And yeah, starting from next week, we will discuss about these few topics, and then we will move to the final part of this lecture series, the premium calculation, in the upcoming 2 weeks. And since we have completed the annuity calculations and the other benefit present value calculations,